Well, in our discussion about functions, the functions are something that we're quite frankly used to dealing with in the past. We just may not have called them functions, and we may not have used the special function notation. And there are many definitions of a function that all basically say the same thing. A function, simply put, is a rule that associates exactly one value with that of some given value. We can think of the given value as input. We can think of it as input. And associated with that is a resulting value, which we would think of as the output. Now, when we're talking about variables, we call the input the independent variable, and we call the output the dependent variable, because it depends on the particular input. Now, what was said a moment ago is when we're given an output, we always expect the same. When we're given an input, pardon me, we're always expecting exactly the same output. If we're giving a 3 and we get a 9 one time, we don't get another value a different time. So that's what I meant up here by exactly one value once we're given a particular input value. The output is one specific value. And we usually see these given by equations. See, it's usually a rule. The rule is an equation. For instance, y is equal to 3x plus 1. Well, the x is the input, and the y is the output. So when we put a 2 in for x, we always get a 7 for y. We don't put a 2 in for x one time and get a 7, and a 2 in for x a different time according to this rule and get something besides 7. So that's the idea behind what a function is. Now, one of the things that we might do is we might be interested in determining whether a particular equation is in fact a function. So as we're determining whether an equation is a function, in the example we had above, determine if the equation y equals 3x plus 1 is a function, what we're concerned about is when we're given a particular value of x. And by the way, we say, in this case, we say y is a function of x. Okay. And the idea is no matter what x we choose, we'll get one and only one y. And that's very clear just from the equation. No matter what x we choose, we're going to multiply it by 3 and then add 1, and that will always result in 1y. So 1x gives 1y. Results in 1 and only 1. 1 and only 1y. So, yes, it is a function. Well, next we'll look at another example where we don't have y as a function of x. So you can see here what we're asked to do is to determine if the equation x squared plus y squared equals 4 defines y as a function of x. And to do this, we must solve for y. Well, when we do that, of course, first we'd solve for y squared. That is, we would subtract x squared from both sides. And then to solve for y, we'd have to say y is plus or minus the square root of 4 minus x squared. Now the problem here is once we choose a particular valid x, then we're going to have a y that is positive and a y that is negative. For instance, if we choose x to be equal to, let's just say 1, then we would get y is equal to plus or minus the square root of 4 minus, and when we square 1, we get 1, so y would be plus or minus the square root of 3. So that means 1y, okay, 1x gives 2 y values. And so it cannot be a function. So y is not a function of x. Remember, to be a function, 1x has to give exactly 1 y value. One valid x has to give exactly 1 y value. So this is not a function. This equation does not define a function. Well, one of the things that we really need to be concerned about is what we call function notation. And we're going to see a lot of this function notation if you haven't seen it in the past. And let's take, for example, y is equal to 3x plus 1. That's the function that we started with. And function notation is going to look a little bit like that, but also a little different. We replace the y and call this thing f of x. Okay. So f of x, and by the way, we read this as not f times x, read this as f of x. And f is the name of the function. And let's take a particular situation, we might say. So, in other words, this gives us a formula, okay? F of x represents y. Or, better put, it represents the output when given the input x. That's really what f of x represents. So for instance, f of 3 represents the y value when x is equal to 3. See, that's the x value, the 3 is, and the whole piece is the y value. So another way to state this is, what is y when x is 3? That's what f of 3 says. What is y when x is 3? So we want to get used to this notation. So we do some evaluations. Let's do that on the next page. Okay, the idea of evaluating a function is to interpret f of. You know, in this case, we're given a function f of x is equal to 1 plus x minus 2x squared. And we're to find the following values. And we'll start with f of negative 2. But remember, what this really means is, what is y when x is negative 2? Because f of negative 2 represents y. Remember that. This represents y. That's a big deal. But what we would simply do is we put the negative 2 value in for the x's. The x, the negative 2, represents x. Okay, so we have f of negative 2. Well, we would just replace in the formula every x with a negative 2. So we'd have 1 plus our x value of negative 2 minus 2 times our x value squared. And our x value is negative 2. So we would replace that x with negative 2. And then we just do some calculations. Of course, 1 plus negative 2 would be 1 minus 2. And then negative 2, we have again, when we square negative 2, we get a positive 4. So this is going to be 1 minus 2 minus 8. And when we do that calculation, we should get negative 9. So f of negative 2 is nothing more than negative 9. Of course, f of 0 would be, we replace each x with a 0. So we'd have 1 plus 0 minus 2 times 0 squared. And when we calculate that, we would simply get a 1. And of course, we could do this with fractions as well. What becomes a little more of an issue is when we replace x with another letter or expression. Now, for instance, if we replaced x with an a, we would simply, if we want to know what f of a is, that means we replace each x with an a. So f of a would be 1 plus, well, we replace x with an a, so we have plus a, minus 2 times, we're replacing x with an a, so we would have a squared. Now, it becomes even more confusing when we replace the x with an expression, and maybe an expression involving x itself. So we have to be real careful that what we really are understanding about this happens to be our input. Okay, this is our input. And let me come back to the function before we do this. You know, we say f of x is equal to 1 plus x minus 2x squared. But that's really just giving us the format. It's kind of like a recipe. Whatever goes here has to be in this position and in this position to calculate. So we could have said something like f of box is equal to 1 plus box minus 2 times whatever is in the box squared. But of course that would be elementary, and that's not the way we deal with it. But when we want to know f of x plus 1, see, that is our input. And so our formula tells us, well, what do we do to our input? Well, before we call our input x, but we just have to represent our input. Okay, what do we do to it? We take 1, we add our input, which is x plus 1, then we say minus 2 times our input squared. And of course our input is x plus 1. So we just get used to replacing, it's just a substitution. Now, to calculate that, we need to do some work. So we would have our 1 plus our x plus 1 minus our 2 times x plus 1 squared. Now, of course, we need to figure out what x plus 1 squared is, and we would simply use FOIL to do that, and I know you know how to do that, but I'm going to remind you. We'd multiply the x's together, we'd get x squared. Multiply the x and the 1 together, we'd get plus x. Multiply the 1 and the x together, we'd get plus x again. Multiply the 1 and the 1 together, and we'd get plus 1. So we end up with x squared plus 2x plus 1. So when we're evaluating f of x plus 1, we have the 1 plus the x plus 1, that was the replacement for x above, and then minus 2, but when we square x plus 1, we get x squared plus 2x plus 1. And so the negative 2 is going to multiply that result of squaring x plus 1. And now we just begin to simplify. The x plus 1 parentheses in that first case are not really necessary. We'll distribute the negative 2. We'll get minus 2x squared. We'll get minus 4x, and we'll get minus 2. And then when we combine all of those terms together, let's see, we have a 1 plus a 1 and a minus 2, which is 0. So this 1 and this 1 and this minus 2 add to 0, don't they? And then we have this x and this minus 4x, which will be minus 3x. And then, of course, we have this minus 2x squared left over. So f of x plus 1 is negative 3x minus x squared. Like I said, this is some of the most confusing kinds of things that we have to deal with occasionally, but we just deal with it as we need to. Let's do another couple of examples, and then we'll move on to something else. Here we're asked to evaluate f of negative x. And so let's remember what f of x in general tells us to do, okay? It says, we'll take 1, add the input, and this time the input is negative x, and then minus 2 times the input squared, and this time the input is negative x. So f of negative x will be equal to 1 plus minus x is minus x, minus 2 times, and when we square negative x, we just get x squared, don't we? So that's the result of squaring negative x. So the result here will be 1 minus x minus 2 times x squared, or minus 2x squared. So again, we just have to get used to the different possibilities that we might see. Let's do this last one. Evaluate f of 2x. Well, remember what we're going to do. We're going to replace each x in the formula. Okay, this is the way the formula looks like, with our input 2x. So instead of putting an x in this position, we replace x with 2x, so we replace it with 2x all the way through. And then we evaluate. Well, 1 plus 2x isn't a big deal, but when we square 2x over here on the right, we'll actually get 4x squared, won't we? So when we simplify, we get 1 plus 2x, and then finally minus an 8x squared as we finish that out. Now, I said one more, but let me illustrate something here that's very important. What is this, G? Now notice above, and it's a very important piece to recognize here. Notice above that f of 2x we just calculated as 1 plus 2x minus 8x squared. And now I want to evaluate 2 times f of x. And so you see there's a different placement of where that 2 is. Now, what I want you to know is that we were already told what f of x is. So this is just saying 2 times our f of x value. And our f of x value we were given as 1 plus x minus 2x squared. So all we're doing here is multiplying 2 and f of x together. That's different than what we did in part f above. So here we actually distribute that 2. We'll get 2 times 1, plus, which is 2, plus 2 times x, which is 2x, plus 2 times negative 2x squared, which is minus 4x squared, isn't it? So we get a completely different result based on where that 2 was. Now, let me also point out, f was the name of the function. And remember, we said f of x is 1 plus x minus 2x squared. Now, other names are usually, not always, but are usually done by lowercase letters. Other names are usually maybe like a G and an F. A G and an H. They can be any names, but my point is F, G, and H are the most common names for functions. And so instead of saying f of x, we could have said g of x is equal to 1 plus x minus 2x squared. Or we could have said h of x is equal to 1 plus x minus 2x squared. And the point of it is the name of the function is not important. It's the rule on how we calculate y that's important. So in all three of these cases, although we're using different names, the results are always the same. And that's the important part. What this does is give us a rule for how we calculate an output given a particular input. And if the rule's the same, then basically the functions are the same, whether they go by a different name or not. So the domain of a function is something that we're asked for many times. And, there's a lot of ways this is described as well. But simply put, the domain of a function is the set of all possible inputs for the function. That is, inputs that make sense and give a resulting real number or real value for y. Now, our independent variable is not always called x, but in the beginning we kind of stick to that idea just so that we have consistency. So the domain could be thought of as all the possible x values that can be used in the function. Now, there's a similar discussion that's called when we talk about the range of a function, and the range of the function is all the possible outputs. And the range is much more difficult sometimes to determine unless we're looking at a graph. But for now, we're just interested in finding domains. So let's look at a few examples. Find the domain of f of x is equal to 3x plus 1. Okay, now here it's very simple. It's so simple it seems difficult. I mean, what x's can we use? Can we use x that's a positive number? Well, sure. We just multiply by 3 and then add 1. Could we use x's that are negative numbers? Sure. Could we use an x that's 0? Sure. Could we use x's that are fractions? Yes. Would we use an x value like pi? Well, yeah, then f of pi would just be 3 times pi plus 1. So the domain here is all real numbers. Now, sometimes in my math lab, we're not going to be able to enter our answer that way. Okay, that's the domain. And probably what we'll need to do is write this in interval notation. And so the way we write all real numbers in interval notation is the set of numbers from negative infinity to infinity. So that's not a point, that's an interval. And it's referring to the real number line. See, here's the real number line, and we can choose all the numbers all the way to the left and all the way to the right. There's where 0 is. So we choose all real numbers. That's the idea of that notation. Let's look at another. Well, here we're to find the domain of the function g of x is equal to x over x minus 2. And so this says whenever we're given an input, we put that, just as an example, g of 1 is equal to, well, what do? We replace x with 1, so we'd have 1 on top divided by a 1 minus 2 on bottom. And of course, that's 1 over negative 1, which is just negative 1. So 1 is an all right value. Now, what I'm getting to eventually here is if we tried to use an x value of 2, we would have 2 in the numerator, but the denominator would be 2 minus 2. And that would be 2 over 0, and that's undefined. And so you see that x being 2 would not be allowed. X is not allowed to be a 2, otherwise we get a problem. And in fact, that's the only thing we're concerned about here. Any x is okay. See, g of 0 would be okay. If we let x be 0, that would be okay, because we'd have a 0 on top and a 0 minus 2, a 0 for the numerator and a 0 minus 2 for the denominator, which is 0 divided by negative 2. But we can divide into 0, we can't divide by 0. So this is 0, so x equals 0 is okay. Up here, x equal 1 was okay. X equal 2 is not okay. And as we think about this, then any x value is going to be all right unless an x value causes the denominator to be 0 here. And so the way we would write this is the domain, we'd say the domain here is equal to the set of all x's. This is called set builder notation. The set of all x's such that, that vertical line is read as such that this condition is true. And the condition that has to be true is x can't be 2. That's the, in other words, that's telling us every x is all right except 2. Now, if we were going to write this in interval notation, okay, we have a little bit more of an issue to deal with here. This is the easiest way to write it. But if we're writing it in an interval notation, let's think about what we have. Let's look at the real number line. Here we go. And somewhere on the real number line is the value 2. Now the value 2 is not allowed, but any other x is allowed. So all the x's to the left and all the x's to the right. But all the x's to the left means from negative infinity up to 2, and we put parentheses around 2 because it can't be included. And then all the values from 2, but not including 2, all the way to infinity. That's what's going on out here. This is what's going on out here. And then we would put a union between those two to say it's the set of all the values between negative infinity and 2, along with all the values between 2 and infinity. So that symbol there, that U, is the union symbol. And this is the way we would write our domain in interval notation. That brings us to maybe another one where let's look at find the domain of, let's say, h of x is equal to x minus 1 over x squared minus 16. Now, we have more or less the same situation here. That it doesn't matter what x we choose, provided it doesn't cause the denominator to be 0. We can't allow the denominator to have the value 0. And so what we end up doing is looking at the denominator and seeing what causes it to be 0. See what causes it to be 0. And so we would solve an equation. And here we could solve that equation one of several ways. In this case, we could just say, well, x squared would be equal to 16. And when is that true? Well, that's when x is plus or minus the square root of 16, or when x is plus or minus 4. So there's two different values of x that will cause that denominator to be 0. One is positive 4 and the other is negative 4. And so the domain will be any values of x except those two. So we'd say the domain is the set of all x's such that x is not equal to negative 4 and x is not equal to positive 4. That's the domain. Now in interval notation, this is what we'd have to write. Okay, the domain would be the set of all x's from negative infinity up to negative 4, union with all of those from negative 4 up to positive 4, union with all those from positive 4 to infinity. And all we're doing is leaving out negative 4 and positive 4, making sure that we're including everything else. See, here's more or less what I did in my head. Here's the real number line. There's negative 4. Here's positive 4. Well, we've got to include all of these numbers, but we can't include this one and we can't include this one. So here we have negative infinity up to negative 4. And in between here, we have from negative 4 to positive 4. And then out here, we have from 4 to infinity. So we're leaving out the -4 and the +4 there. So this is the way we would write the domain in interval notation. Sometimes that's what we'd have to do in my math lab if we're using that software. Okay, let's see then. Let's look at a different type. Maybe in this case, find the domain of, we'll call this function capital F. Capital F of x, which is equal to the square root of, let's say, 3x minus 12. Now, here we're dealing with a couple of different issues. I mean, we're dealing with a different kind of issue. And so what I would tell you as we're thinking about this, remember, we're looking for x's that we're allowed to use. And so I'm going to first start out saying that if we take the square root of 0, that's okay. That's just 0. And if we take the square root of a positive number, that's okay. But if we take the square root of a negative number, that's not okay. It's a complex number, and we have to get real number results. So we need to make sure that what we're taking the square root of is either 0 or positive. See, we've got to ensure that our x's make sure that we have the square root of 0 or the square root of a positive number. Well, what are we taking the square root of? 3x minus 12. And so we have to either make sure that's equal to 0 or positive. Now, the way we say positive is we say greater than 0. That's positive. And if we say 0, that's equal to 0. So all we're doing is making sure that what's under the radical, 3x minus 12, is greater than or equal to 0, meaning it's either 0 or positive. And so we simply solve this inequality. Now, remember how we would solve an inequality like this. We'd add 12 to both sides, and then we'd divide both sides by 3. And since we're dividing by a positive number, then the sign, the direction of the inequality does not change. And so we'd get x is greater than or equal to 4. So the way we would write the domain here, now remember, those are x's that are good values. See, those are x's that are good values because that makes us have a square root of something that's either 0 or positive as long as we choose our x's that are 4 or larger. So in the set builder notation, we'd say the set of all x's such that x is greater than or equal to 4. Now in interval notation, we have to approach this yet a little differently. Okay, and so what we're thinking of is the real number line again. What x is this is the x values, okay? So we find out where 4 is, there's where 4 is, and we can choose x's that are either bigger than 4, so that would be to the right of 4, or equal to 4. And equal to 4, normally we put a bracket around the 4 to say 4 is included. And so if we just look at that little diagram, then that's we just more or less illustrate that diagram, but this time instead of parenthesis around 4, we put a bracket saying 4 can be included. And so it goes from 4 to infinity, but since infinity is not a number, we can't include it. So parentheses means not included, and we never include infinity. It just tells us that we're going to the right forever. Let's do one more of these domain problems. Here we've got a function g of x that is 5 over the square root of x minus 7. And here we have a couple of compounding issues. One, we have a fraction, and so the denominator cannot be 0. It is not allowed to be 0. Okay, well, the denominator is the square root of x minus 7. And the only way that's going to be 0 is that's 0 if x itself is 7, because then we'd have the square root of 0, wouldn't it? But wouldn't we? What we could do is say we could say, well, when is, whoops, x minus 7 there. When is that equal to 0? And we could square both sides. And we'd get, well, then x minus 7 would have to be 0. And that would be when x is equal to 7. Now that's when it's equal to 0, and we're not allowed, we can't let that happen. So that means x is not allowed to be 7. Okay? That is, x is not 7. Now, I'm kind of going in a circle here because there's another issue. The square root of x minus 7 has to be positive then. Must be, excuse me. We have another problem when we're dealing with the square root of x minus 7. Now, generally, that means that that x minus 7 underneath the radical must be either positive, that's greater than 0, or equal to 0. But we can't let it be equal to 0 because then we would have a denominator of 0. So in this case, we've got to make strictly the case that x minus 7 has to be greater than 0, not equal to 0. And I've seemed like I've gone into kind of a strange circle here. So the bottom line, rather than what we did before in saying x minus 7 is greater than or equal to 0, we must have strictly x minus 7 is greater than 0. Because if it was equal to 0, we'd have the square root of 0, which is 0, we'd have the 0 in the denominator. And of course, this means x is strictly greater than 7. So the domain here would be the set of all x's such that x is greater than 7, not greater than or equal to 7. And in interval notation, that will be the interval from 7 to infinity. And the difference here is we don't put the brackets around 7 this time. So here's what we've got. 7 is here, and we shade to the right because we're greater than 7, but we are not equal to 7, and the way we show not equal to 7 is we put a parenthesis around it. So that's the way we would write the answer in my math lab if we were forced to do so. Well, a very important part of Calculus 1 specifically is dealing with difference quotients. And for right now, we don't need to know the significance of the difference quotient. We just need to know how to calculate it. And so let me tell you what the difference quotient for the function f is about. A quotient, of course, means fraction. So it's more or less a little formula here. The difference quotient for f, for a function f, okay, for a function f, is this fraction. The numerator is f of x plus h minus f of x, and the denominator is just h. So we use the definition of our particular function to calculate each component. And you can see, of course, for us to calculate this fraction, one of the things we need to know is that value f of x plus h. So remember that f of x is given to us here. It's 3x plus 1. So if we want to calculate f of x plus h, we have to remember that we're replacing x with x plus h. And the function f says multiply the input by 3 and then add 1. Well, this time the input is x plus h. And so when we simplify by distributing that 3, we'll have a 3 times an x plus a 3 times an h plus a 1. So that's what f of x plus h is. Now, the numerator of that fraction is given by f of x plus h minus f of x. And so we just put in place of f of x plus h what we calculated above, 3x plus 3h plus 1. And we're subtracting f of x, which was given to us as 3x plus 1. Remember, this part is the f of x plus h. And this part is simply the f of x. And then we just use some algebra to simplify. These first parentheses I put for emphasis. They're not necessary, really. The second parentheses I put because they are necessary, because we're subtracting something that has more than one term. So we need to distribute that subtraction sign. We get minus 3x and minus 1. And that then we can simplify because we have this 3x and minus a 3x. We have this 1 and minus a 1. So we're left with just 3h. So the difference quotient then is the fraction f of x plus h minus f of x divided by h. And from above, we figured out the numerator, f of x plus h minus f of x. We just saw that it was 3h. And our denominator is h, so when we simplify that fraction, the result of the difference quotient is just the constant 3. Now, the next example is going to be a little more involved because we'll have a more complicated function. But let's do that on the next page. Okay, as I said, our difference quotient here is going to be more complicated because our function f of x is more complicated. But remember what the difference quotient is. Okay, whoops. Now, I'm not going to give the result. I'm more or less giving the format. The difference quotient. So I'm having all kinds of problems. Is the result of creating the fraction and simplifying f of x plus h minus f of x, all divided by simply h. And so there's several steps here. One, we need to calculate f of x plus h given our particular function this time. Then we need to calculate the numerator, okay, which is f of x plus h minus f of x. Then we need to calculate and simplify the fraction. And of course, the f of x plus h, the numerator of the fraction, we've calculated in step 2. And so we're just creating the fraction, and then we'll simplify that fraction. So, f of x plus h in this example, remember, what does f do? It takes 3, it adds 2 times the input, and then it minuses the input squared. Now, in the formula, the input's x, but in our case here, the input is x plus h, so it's 2 times an x plus h minus an x plus h being squared. Now, I want to do something here. I'm going to box this in, but it's this x plus h squared that I want to deal with, okay? Because we're going to need to do that in this calculation, aren't we? So that means x plus h times x plus h. Now, when we do this calculation, we'll get x times x, that's x squared, and then we'll have plus x times h. Now, it's normal to put the multiplication of letters in alphabetical order. So rather than saying x times h, I'm going to say h times x. And then we'll move here and we'll multiply the h times the x, so we'll have plus, in alphabetical order, that's hx. So you see that we have 2 terms just alike. And that's the reason we do this in alphabetical order, so when we will recognize they're the same. And then finally, plus h times h, which of course we call h squared. So this ends up being x squared plus 2 of these hx's plus h squared. Okay. Now, in the future, I may just write that down, but I think for the first time through, it's important to see where that came from. So back to f of x plus h. It was 3 plus 2 times x plus h minus x plus h squared. And as we simplify that, we'll distribute that 2 times x plus h, that's a 2x plus a 2h. And then we're going to subtract something, but what we're subtracting is the result of squaring x plus h. So we need to put that result in parentheses, and when we did that squaring, we got x squared plus 2hx plus h squared. So now we need to distribute that subtraction sign. We get minus x squared minus 2hx and minus h squared. Now that's a big, long string of letters, but it doesn't look like there's any simplification that we can do because there's no like terms, are there? So we move on to the next step. And the next step is to calculate f of x plus h minus f of x. So we need to put in f of x plus h, and that's that step right above us. F of x plus h is 3 plus 2x plus 2h minus x squared minus 2hx minus h squared. And then we need to subtract what f of x is. Well, f of x was given to us as 3 plus 2x minus x squared. So we do a little algebra here to simplify. Those first parentheses, I put in to emphasize that all was f of x plus h. So I'm simply removing those parentheses, and then I'm distributing this negative sign. So I'll have a minus 3, a minus 2x, and a plus x squared. Now I think that I can, in fact, simplify because I have a 3 minus a 3. And I have a 2x minus a 2x. And I have a negative x squared plus an x squared. And so when the dust settles, it looks like I have a 2h minus a 2hx and minus an h squared that's left. That's all that's left. So our next step is to calculate the fraction and simplify. Now remember, this is the quotient. The difference quotient is this fraction. In the numerator, simplified to that step above, 2h minus 2hx minus h squared. And we're dividing by h. Now the only way we're going to be able to simplify is by reducing the fraction. That is, canceling that h that's in the denominator. And the only way we can do that is if we have a factor of h in the numerator. And we notice that each term in the numerator has an h in it, so h is a common factor that can be factored out. So we'll factor out an h in the numerator. H times 2 is how we get a 2h, minus h times a 2x, that's 2hx, and minus h times an h. That all we've done is factor out an h from each of those terms. Okay? If I multiply that out, I get 2h minus 2hx minus h squared. And so now I see that I can reduce, I can cancel, and that leaves me with 2 minus 2x minus h. In other words, and I've run out of room here, when we simplify this fraction, we get 2 minus 2x minus h. And that's the result of simplifying our difference quotient. Well, that ends my discussion on functions. We'll start the next section with a different discussion, but for now, that's all we're going to do about functions. Good luck on your homework.